Dear ladies and gentlemen, I would like to present an alternative concept of the plasticity of solids, which is based on the specific features of their electronic structure. According to this concept, the mechanical properties of solids, such as plasticity and strength, depend on the spatial distribution of the density of their valence electrons. This distribution determines the type of interatomic potential, either spherically symmetric or asymmetric. Slide 3, Distribution of the valence electron density in solids. In the case of a spherically symmetric interatomic potential, the crystal lattice undergoes compression, which leads to its instability and plasticity. Conversely, an anisotropic distribution of valence electron density results in an asymmetric interatomic potential. This is typical of covalent and other directional chemical bonds. In such cases, the crystal lattice is not compressed, and the atoms form a stable crystal structure. These solids exhibit low or zero plasticity and electrical conductivity. Such materials include semiconductors and dielectrics. When the crystal lattice is compressed, delocalization of the electron gas occurs, and the valence band overlaps with the conduction band. Therefore, lattice compression gives rise to the high plasticity and electrical conductivity characteristic of metallic bonding. Environmental parameters such as pressure and temperature have a significant influence on the stability of the crystal lattice. Slide 4, Causes of crystal lattice instability. To investigate the causes of lattice instability, well-known experimental and theoretical data were analyzed. These show that under high hydrostatic pressure, all solids exhibit plasticity and electrical conductivity. This indicates a transformation effect. Under sufficient hydrostatic pressure, all solids acquire metallic properties. Given the inherently high plasticity of metals, a hypothesis was proposed that internal forces exist in metals, capable of compressing the lattice. The cause of this compression is a spherically symmetric, or nearly symmetric, interatomic potential. With such a potential, long-range attractive forces between distant atoms are balanced by repulsive forces between nearest neighbors. As the lattice compresses, the potential energy of the atoms increases, Figure 1, and the atoms occupy positions that do not correspond to their minimum potential energy. This is the root cause of crystal lattice instability. Compression plays a key role in understanding this instability. Slides 5 to 6, Determination of the interatomic lattice distance. Slides 5 and 6 present the results of a theoretical study of a two-dimensional crystal lattice conducted using molecular mechanics. It was found that a two-dimensional lattice with a spherically symmetric interatomic potential undergoes compression. This is indicated by an interatomic distance 6.4% shorter than the equilibrium distance in a diatomic model of a solid, Figure 2, Slide 5. Studies of shear resistance in unstable crystal lattices show that no energy is required to shear atomic planes, Figure 4, Slide 6. In this state, the lattice is held together only by the surface atoms. Such a crystal is in a state of unstable equilibrium, that is, in a metastable state, because its atomic planes shear under very small forces, comparable to those required for dislocation movement, Figure 4, Slide 6, resistance to shear of atomic planes in an unstable lattice. Slide 7, Alternative and classical concept of plasticity. The classical concept assumes that the ideal crystal lattice of solids is stable, Figure 5a. Therefore, considerable energy is required to shear atomic planes. Plasticity in such solids is attributed to the presence of dislocations, which are local unstable regions in a stable lattice. In the absence of dislocations, plastic deformation is considered impossible. By contrast, the alternative concept proposes that the crystal lattice of plastic solids is unstable, Figure 5b, which explains of their plasticity. Slide 8, Alternative crystal model and its plastic deformation. Figure 6 presents a model of a crystal with an unstable lattice. The crystal has a two-phase structure. One phase consists of interior atoms, white circles, which form an ideal crystal lattice. These atoms occupy positions that do not correspond to their minimum potential energy. They are held in place by surface atoms, black circles, which belong to a second phase with a different structure and properties. Such a crystal is metastable. When tensile stress is applied, figure 6a, it primarily affects the surface atoms, while the interior atoms do not experience this stress. Once the stress reaches a critical level, interatomic bonds between the surface atoms break. At the rupture point, atomic planes, figure 6b. Shear by one or more interatomic distances via a sliding mechanism. The energy of this displacement is compensated by a decrease in the potential energy of the atoms. As a result of this shear, the interior atoms move to positions of minimum potential energy. Further displacement from these positions requires significant force, indicating local strengthening. Thus, sliding transfers to other atomic planes that have not yet undergone displacement. Another possible scenario, figure 6c, involves the simultaneous shear of several atomic planes by a distance shorter than the interatomic spacing. This corresponds to the twinning mechanism. In the case of twinning, plane shear can occur without rupture of the surface layer. As the stress continues to increase, further ruptures occur, leading to repeated plane shears. Therefore, the plastic deformation process proceeds as a sequence of aperiodic atomic plane shears. This process is illustrated step by step in Figure 7, Slide 9. Slides 9 to 10, Difference between models of plastic crystals. It is important to emphasize that plastic deformation, as described by the dislocation model and the alternative model, proceeds in fundamentally different ways. 1. Deformation mechanism. In the dislocation model, shear of atomic planes occurs through the sequential movement of individual atoms, figure 7a, slide 9, and the lattice is restored after the passage of the dislocation, figure 7a, position 4. In the alternative model, entire atoms shear simultaneously, disrupting the lattice structure, figure 7b, positions 3 and 4. 2. Hardening mechanism. In the classical model, hardening arises from the multiplication and interaction of dislocations, which impede each other's motion. In the alternative model, once atoms shear from unstable to stable positions, further displacement requires stresses approaching the theoretical strength. This leads to hardening and causes the shear to transfer to other planes, figure 7b, position 4. 3. Scope of applicability. The classical dislocation-based model explains only the elementary act of plastic deformation, namely, the shear of a single atomic plane by one interatomic distance. To explain further deformation, various additional mechanisms are needed: screw dislocations, twinning, grain boundaries, helical, partial, Lomer, Cottrell and prismatic dislocations, dislocation sources, e.g., Frank-Reed, and cross-slip mechanisms. In contrast, the proposed model explains atomic plane shears without invoking any defects, since the crystal lattice is already unstable. The explanation of easy shear is therefore simpler and more general. Despite these differences, the two models share several features. The cause of plasticity is crystal lattice instability, local in the classical model and global in the alternative model. Plastic deformation results from the transformation of an unstable structure into a stable one through atomic displacement to positions of lower potential energy. Plastic deformation proceeds through mechanisms of slip and twinning. Shear of atomic planes occurs under low stress levels, as in the dislocation model. Slides 11 to 16, Experimental confirmation of the proposed model. First confirmation. Slide 11, Dependence of single crystal strength on cross-sectional size. According to the proposed model, the strength of a plastic crystal is determined by the strength of its surface layer and therefore depends on its cross-sectional size. For small diameters, the yield stress should be high and decrease with increasing diameter, following the predicted curve, figure 8, slide 11. This prediction is supported by experimental data, figures 9 and 10. The yield stress of thin, whisker-like crystals is extremely high. However, as the diameter increases, the yield stress decreases because the surface effect diminishes. For diameters above 50 microns, it approaches the yield stress of conventional metals. In polycrystalline metals, the yield stress also decreases with increasing grain size, Figure 11, Hall-Petch relationship. It is worth noting that, according to dislocation theory, the high strength of whiskers is attributed to their perfect internal structure and is often cited as evidence supporting the classical model. However, such interpretations overlook the role of the surface, which constitutes a two-dimensional defect. Second. Slide 12, Existence of massive metal single crystals with low yield stress. According to the predicted trend, a further increase in crystal size should reduce the yield stress to near zero. This is confirmed by artificially grown, massive, high-purity single crystals with nearly perfect structures, Slide 12. These crystals exhibit extremely low yield stress, approaching zero, which provides direct evidence of lattice instability. This conclusion is supported by statements from leading researchers. One such statement reads: Plastic flow in metallic single crystals begins at any small stress. This means that the true yield point of these crystals is equal to zero. Slide 12 presents additional similar quotations. The instability of massive metallic single crystals explains both their absence in nature and the difficulty of growing them in laboratory conditions. This phenomenon is not widely known, likely because it contradicts the classical concept of plasticity. Third. Slide 13, High strength of defective whiskers. Another important experimental observation is the high strength of whiskers with defects, often greater than that of defect-free crystals. As mentioned earlier, the strength of an ideal whisker is due to its surface layer, while the interior does not carry load. However, during plastic deformation, atoms move to positions of lower potential energy, leading to hardening. If a thick whisker is carefully deformed, its strength should significantly increase. This hypothesis has been confirmed. Figure 13, Slide 13, shows the plastic deformation curve of a thick copper whisker, curve 2, which reached a high strength, 1200 MPa, exceeding that of a thin, undeformed whisker, curve 1. Additional data presented on Slide 13 confirm that deformed whiskers and whisker-like structures with defects can also exhibit very high strength. This contradicts the classical view that the high strength of whiskers is solely due to their perfect structure. Fourth. Slide 14, Jerky flow, Poitevin-Le Chatelier effect. Evidence of simultaneous atomic displacement during slip and twinning is found in the jerky flow observed during tensile testing of metals, Figure 15, Slide 14. This is known as the Poitevin-Le Chatelier effect. The jerky deformation, visible as stress jumps, is accompanied by temperature jumps, Figure 17. Figure 16 shows a single stress drop and simultaneous temperature rise, caused by the release of heat during atomic displacement to lower energy positions. These events are also accompanied by bursts of acoustic emission, supporting the interpretation of simultaneous atomic movement during slip. Fifth. Slide 15, Confirmation of crystal lattice compression. The hypothesis of lattice compression has also been expressed by several researchers. For example, W. Pearson wrote, Analysis of nearest neighbor diagram suggests that, in metals with the A2 structure, which are easily compressible, the atoms are slightly deformed in the direction of contact with the 8 nearest neighbors. This explains the shortening of interatomic distances in contacts with 6 atoms, the second neighbors, where the experimentally observed distances are slightly shorter than the normal atomic diameter. Slide 16, Dependence of metal's strength on defect density for both models. This slide presents the dependence of metal strength on defect density according to both the classical and alternative models. In the classical model, defects, dislocations, have a dual effect on metal strength, Figure 14a. A decrease in their number increases strength, as the structure approaches the ideal. Conversely, an increase in dislocation density also strengthens the material, this time due to enhanced resistance to dislocation motion. In the alternative model, however, the effect is unambiguous. Figure 14b, defect-free crystals have low strength, and increasing the number of defects leads to higher strength. Slide 17 to 20. Effect of temperature on the stability of the crystal lattice. A number of additional experimental confirmations are related to plastic deformation at low and high temperatures, which appears anomalous from the perspective of classical theory. Figure 19 presents the results of theoretical studies on the temperature dependence of crystal lattice stability. It was found that as the temperature increases, the interatomic distances increase, and the crystal lattice gradually stabilizes, curve 2. At a certain temperature, curve 3, the crystal lattice becomes fully stable. First confirmation. Slide 18, increase in plasticity with decreasing temperature in the region of low and moderate temperatures. As the temperature decreases, the crystal lattice loses its stability, which, according to the alternative model, should lead to an increase in the plasticity of pure metals. This conclusion is supported by experimental stress-strain diagrams for aluminum and copper, shown in Figure 20. It was observed that when the temperature decreases from 350 K to 4 K, the plasticity of aluminum and copper increases, as indicated by the increase in their elongation. Slide 18 also presents other experimental data confirming that the plasticity of metals increases with decreasing temperature. These experimental findings contradict Seeger's theory, which asserts that plasticity should increase only with rising temperature due to the enhanced mobility of dislocations. Second. Slides 19 and 20, decrease in plasticity in the high-temperature region. In the high-temperature region, the observed increase in metal plasticity with temperature, contrary to theoretical expectations, is explained by a change in the plasticity mechanism, from intragranular to intergranular amorphous diffusion. According to theoretical studies, the plasticity of metals should gradually decrease with increasing temperature, and beyond a certain point, metals should lose their plasticity altogether. Above the so-called equicohesive temperature, plastic deformation of the intragranular material becomes limited. The lack of plasticity within the grains at elevated temperatures gives rise to brittle zones, known as plasticity dips, Figure 21. This phenomenon occurs in the temperature range where the grains have already lost their plasticity, while the intergranular amorphous diffusion mechanism has not yet become active. If the temperature ranges of these processes overlap, the plasticity dips do not appear. Slide 21, Advantages of the alternative concept of plasticity. The alternative concept offers a fundamentally new and much simpler explanation of the plastic deformation process. It accounts for the anomalously low shear resistance of massive metallic single crystals, causes of strengthening during plastic deformation, the dependence of shear resistance in microsingle crystals, whiskers, on cross-sectional size, the anomalously high strength of deformed whiskers, unexplained by the dislocation model. It also explains the significant difference in plasticity between metals and covalent or ionic crystals, even in the presence of dislocations in both. The selectivity of atomic plane slip, dislocation motion, along specific crystallographic directions. The phenomenon of brittle, non-plastic materials becoming plastic under high hydrostatic pressure. The existence of plasticity dips in metals and their alloys at high temperatures, as well as the anomalous, from the viewpoint of the dislocation model, decrease in yield strength and increase in plasticity at low temperatures. The correlation between different phenomena, such as plasticity and electrical conductivity. The anomalously high plasticity of nonmetallic crystals, e.g., silver chloride. According to the proposed model, plastic deformation is a physical phenomenon whose essence lies in the movement of atoms into positions of lower potential energy. Plasticity is an inherent property of the ideal crystal lattice in metals, whereas in the dislocation model, atomic plane slip requires the presence of dislocations. Moreover, the proposed hypothesis provides a bridge between two approaches to explaining plasticity, one based on lattice defects, the structural factor, and the other based on the electronic configuration of solids and the type of chemical bonding. Slide 22, Integrality of the alternative concept of plasticity of solids. The alternative concept has been developed on the basis of a vast body of experimental and theoretical data. A number of existing theories and hypotheses are integral components of the proposed concept. These include 1. The dislocation model of Taylor, Orawan, and Polanyi. 2. Max Born's theory of crystal lattice stability. 3. The notion of plasticity as a property of defect-free crystal lattices, early ideas by Frenkel, Stepanov, and others. 4. Physical mesomechanics, academician Panin and colleagues. 5. The model of jerky propagation of plastic shears, the model of incomplete slip by Neverov and Antonenko. 6. The configurational model of matter, academician Samsonov and others. 7. The coexistence of metallic and covalent bonds in pure metals and their two-phase structure, Arkarov, Rosenhain, Belby, and others. 8. The kinetic theory of the strength of solids, academician Zherkov. 9. The hypothesis of the equicohesive temperature, Jeffreys. All of the above are the puzzles that together form the complete picture of the natural phenomenon of plasticity in solids. Therefore, the alternative concept should be regarded as an integral concept of solids plasticity. It is clear, however, that this concept is not yet fully complete and requires further study and development. Thank you for your attention.